Hello everyone, I am Dr. Osman reporting once again from the University of KwaZulu-Natal, South Africa, the premier university of African scholarship. Today's lecture will be a gentle welcome to material balancing in reacting systems, and we will start by looking at the notation as well as how to write out a material balance by taking into account reactions. We will look at concepts such as the consumption and production rate as well as the overall reaction rate and how to include them in material balancing. We will also look at other issues such as the limiting reactant as well as the conversion. Okay, so today's lecture will focus on single reaction systems. So let's get to it. Let's just look at a separation unit just as a benchmark or a comparison. Okay, so that's a separator. We have one feed coming in and perhaps two streams coming out. Okay, and I can number these streams, stream 1, 2 and 3, and as you will know by now, in the case of a separation unit or any non-reacting system, input is equal to output. Okay, and this is true whether we are talking in molar terms or in mass terms. Okay, so we can write a total balance of F1 is equal to F2 plus F3. Or if we have to look at our components, let's say for example we have species I, J and K coming in. We have our mass fraction of species I, for example, in stream 1 multiplied by F1, and that will be equal to mass fraction of species I in stream 2 times F2 plus the mass fraction of species I in stream 3 multiplied by F3. And we can also write this out in terms of moles. Okay, N1 is equal to N2 plus N3, or we can say X1I times N1 is equal to X2I times N2 plus X3I times N3. Okay, so this is just revision for you by now, right? So this is a non-reacting system. You've been looking at this in the past lectures. It's probably quite boring to you at the moment. Okay, we can also write this in terms of a component flow. N1I is equal to N2I plus N3I. Okay, so this is what you already know. Now let's look at a reactor. Briefly, well, you should know this by now. In a reactor, a chemical reaction occurs. Okay, so if I have to feed in certain components, okay, let me just call them A, B, C, or rather A, B and I. Once these components go into a reactor, a reaction occurs and we don't have a conservation of mass for each component. Okay, so let's say for example we have a reaction occurring in this reactor and the reaction is arbitrarily A plus B becoming C plus D, and the small a, b, c, d are my stoichiometric coefficients. So what's coming out of this reactor will be A, B, C, D, and still I. Okay, so in this particular case, I represents an inert, something that's not participating in the reaction. So it goes through the reactor unchanged. Okay, it goes in and it just comes out. Okay, but the amounts of A and B have changed because some of the A and B would have converted into C and D. When talking in total terms, we can still say that if this is stream 1 and that's stream 2, F1 is still equal to F2. Okay, so we will get a total conservation of mass. That will not change. However, the total number of moles will not be the same. It will change. Because now we have a certain number of moles of A and B becoming a certain number of moles of C and D. And depending on the stoichiometry, we may not necessarily have the same number of moles. Okay, and this is true whether we are talking in total terms or in component terms. N1A, for example, will not be equal to N2A. Okay, because some of the component A is being used up in the reaction. So due to these changes, we need to define a term to account for the flow of each component through a reactor. So we can define Ri, or big R, to be the production rate or consumption rate. If we are speaking in terms of our reactants A and B, then R of A and R of B will be a consumption rate because A and B are being consumed. They're being used up. If we are talking about C and D, then R of C or R of D will be a production rate because C and D are being produced. All of the production rates and consumption rates are, however, linked. Okay, and they are linked by the following relationship. Yes, and one more thing is that in the case of A and B, because they are reactants, our R for A and B will be negative, and because C and D are products, the R for component C and D will be positive. Now, if we had to write out our material balance for this reactor, and one thing to note is that when talking about reactors, the reactions are expressed in molar terms. So we almost always speak in terms of moles, not mass. Okay, so if you are confronted with a problem where they are giving you the mass flow of A and the mass flow of B, you will have to convert to moles in order to address the problem. Okay, so let's look at component mass balances, or material balance more correctly. Okay, in the case of component A, so we don't have a case of in being equal to out. Okay, for a separator, input is equal to output. However, in this case, our output is not simply equal to our input. Okay, so if we have to say the general term or the general expression, we can have output is equal to input plus the effect of the reaction expressed by Ri okay, so that's either your production or your consumption rate. So in the case of component A, our output can be expressed in terms of N2A, and that will equal to N1A, what came in, plus whatever happened in the reactor, and that will be represented by our consumption rate, RA. Okay, so it's inevitable that RA will be negative because A is a reactant. Okay, and we can write a similar expression for component B, where RB is also going to be negative. Now let's look at the case of C and D. Okay, for component C, we will have N2C will equal to N1C plus RC. In this case, N1C is equal to 0. There's no C coming in. Okay, so this can be crossed off as 0. And the same can be said for component D. Okay, so this is how we will have to write out our material balances for a reactor. Okay, and we will develop this as we go along. We will develop it for multiple reactions and multiple reactors as well. I've forgotten to mention one component, and that is our inert component, Ni. That will simply be N2I is equal to N1I. Since nothing happens to I in the reactor, it's inert, so the output will be equal to the input. Okay, so the reaction changes the output, whereas if something is inert, it will just go through the reactor and will not change in mass or molar terms. Now, instead of having to find each individual RA, RB, RC, and RD, we can also note that these production or consumption rates are related to each other because our reaction follows a certain stoichiometry. Okay, so for our reaction, AA plus BB giving us C plus DD, the following relationship will hold. We can say that negative RA over our stoichiometric coefficient A is equal to negative RB over our stoichiometric coefficient B, and that will be equal to RC over our stoichiometric coefficient C, and that is equal to RD over our stoichiometric coefficient D. And we can let all of this be equal to small r, which we define as our overall reaction rate. Okay, and this reaction rate will be expressed in terms of moles per hour or moles per second, kilomoles per hour, depending on the situation that we are confronted with. Okay, and each of these consumption or production rates are also in terms of kilomoles per hour or kilomole per second, depending. Note that in the case of our reactants, we regard our stoichiometric coefficient as negative. Okay, and this is where we get our negative. It's actually Ra over negative A is equal to Rb over negative B. I've just taken this negative to the top here to express it as the entire fraction. Okay, and it will of course be positive for our products because our products are being produced. In general, our overall reaction rate can be expressed as the production or consumption rate of any species I over the stoichiometric coefficient of I in our reaction. Okay, the stoichiometric coefficient will be negative for reactants and positive for products. So we can ultimately say that, or we can express all of our production or consumption rates in terms of our stoichiometric coefficient and the overall reaction rate. So for every case, remember we wrote, for example, N1A being equal to, N2A being equal to N1A plus RA. Instead of expressing it in terms of an individual consumption rate, we can write our balances in terms of our overall rate. Note that our overall reaction rate actually becomes an independent variable, because once we find our overall rate, small r, if we know the stoichiometry of the reaction, we can get every other production rate or consumption rate of all of our components. So a key issue becomes finding our overall reaction rate. The reaction rate R is related to our reaction or production, our consumption or production rate. We can also write out this generic balance and note that our R, just switching this equation around, can also be found in the following manner. Okay, and this equation here can be used depending on whether you have the output flow rate of A and the input flow rate of A, and of course the stoichiometry of our reaction. Note that this particular equation will only be valid for single reaction systems, a reactor in which only a single reaction occurs. We will look at reactors where we have multiple reactions occurring in the same reactor, and we will look at that in subsequent lectures, and this equation will ultimately change. We can also rearrange this equation in terms of RA, our production or consumption rate. Okay, and we can see that RA is simply just the difference between our component A coming out of the reactor minus the component A coming into the reactor. Okay, so remember we have, for example, component A coming in at a certain flow rate. It will be consumed at a certain flow rate, at a certain consumption rate, RA, and the remainder will flow out at a certain flow rate, an output flow rate. Okay, so RA is just the difference between our output and input flow rates. Okay, and this is true for RB, RC, and RD as well. Okay, it's just NB out minus NB in, NC out minus NC in, and ND out minus ND in. Okay, so that's true for all components. If we had to write this equation here for components B, C, and D, we can also note that our R is equal to NA out minus NA in over our stoichiometric coefficient, okay, in the negative. It's also equal to NB out minus NB in over negative B. These are because A and B are reactants. If we have information on our products, then it would be NC out minus NC in over C. Okay, that would be positive. Or ND out minus ND in over D. Okay, it's important to note that the overall reaction rate R will always be a positive number. Okay, our consumption rates will be negative. However, they will be offset by taking our stoichiometric coefficients to be negative for reactants. Okay, and our production rates will be positive, and our stoichiometry for our products is positive, so there's no need for any offset there. Now, it's very important, and it may seem that I am just playing around with equations, but it's very important that you yourself actually become very well acquainted with these equations, play around with them as well, because there are many different ways in which information can be given in our different processes and problems that we can be confronted with. And as you can see, there are many different options towards solving a material balance around a reactor. Okay, depending on whether we are given a production or consumption rate, or whether we are being given an overall reaction rate, or whether we are given the actual output and input flow rates. Okay, so in general, we can simply write that for any species I, Ni out will equal to Ni in plus our stoichiometry multiplied by R. Okay, so whenever we are dealing with a reactor, then with a single reaction, this is the form that our material balances will occur in for each component. We can also write it in terms of our production or consumption rates. We can say Ni out is equal to Ni in plus, and replacing our R with any of these, okay, that's Vi times Na out minus Na in over negative A. If we had information for B, then we could have just replaced our R with this equation. If we had information for C or D, we could do the same thing as well. Okay, so there are many different ways in which we can obtain R, and it's very important that you are well aware of them so that you can solve the material balance. Okay, another term that I would like to introduce to you before we look at an example is the conversion. Now, if we consider a typical reactor, it has two or more reactants being fed to it, and we of course get some products. Usually one of the reactants will be a principal reactant or a reactant that's being dealt with in greater importance. And in such a case, we can look at what the conversion of our particular reactant is, our key reactant is, in order to produce the products. Okay, so we can define our conversion for any species, for any reactant. Okay, and our conversion, denoted as Xi, is our input flow rate of our reactant minus the output flow rate of the reactant divided by the input flow rate of our reactant. Okay, and I must stress that this is valid only for reactants. We don't speak of conversion of products, because products are not what's being converted. A product is being formed. A reactant is being converted to a product. Okay, so this is how our conversion is expressed. It's known more accurately as fractional conversion. Okay, and we can just look at what it means. We are considering the flow rate of a particular reactant coming in and the flow rate coming out. Now, if a certain amount is going in and we have a lesser amount coming out, obviously the difference is, of course, what converted. Okay, so this difference here is representative of the amount of reactant that actually converted in the reaction. Okay, and we're dividing it over our input flow rate, and we get a fractional conversion. Also, note the difference between the conversion and our overall reaction rate. I've seen some students confuse this many times. Okay, so it's very important that you get your terms correct and you are able to move around in your equations very accurately. We can express our output flow rate in terms of this form here, or in terms of this form here, and ultimately we can see that this expression can look like this Ni in minus our Ni in plus VIR over Ni in. And this can reduce if we simply open these brackets out. We find that our conversion is equal to negative of our stoichiometric coefficient times our overall reaction rate over our input flow rate. Okay, so we have a relationship between our conversion and our overall reaction rate. I must stress, however, that this is only valid for single reactions. Okay, so if there are multiple reactors occurring in our reactor, then we cannot use this relationship, because when there are multiple reactions, then this relationship here, or this expression here, changes. We have more than one overall reaction rate. Okay, so please don't make that mistake. But for now we are looking at single reactions, so we can use this particular expression. We could write it in the other way in terms of R. It's Xi times Ni in over our stoichiometric coefficient, the negative of the stoichiometric coefficient. Now, in the case of our limiting reactant, recall that when we charge two species into a reactor, perhaps there may be a case where one of the reactants are stoichiometrically less than the other, so we will have one reactant being used up or consumed to absolute completion, and we'll still have a leftover of the other reactant that will be known as the excess. Now, in the case of the limiting reactant, our conversion will be complete. Okay, so we will have an input flow rate, but because our reactant is limiting, it means that all of it will get finished. So Ni out will be 0 and our conversion will be 1. In other words, 100% conversion. And in this case, we can write for the limiting reactant, we have a relationship of R is equal to negative Ni in over our stoichiometric coefficient. Okay, and this will become useful later. We will look at an example on this perhaps. But generally what I can say for now is that if you are confronted with a problem and you do not know which reactant is the limiting reactant, then you can simply calculate the R value for each of the reactants. Let's say if there are only two reactants, A and B, we can find our R using our molar flow rate of A coming in and the molar flow rate of B coming in, and compare the species that has the smallest R value or overall reaction rate implies that the feed is low in content, but the stoichiometric coefficient is relatively high. So therefore, that reactant will be converted completely. It will be used up. It's the limiting reactant. Okay, so basically, when finding the limiting reactant, we can simply calculate R in terms of all of our reactants. Whichever R is the smallest R, that will be the associated limiting reactant. Just to add some numbers to your understanding, let's just consider a real reaction. Okay, the production of ammonia. We have nitrogen plus our hydrogen, 3 moles of hydrogen producing 2 moles of ammonia. Okay, in such a case, we can express R as follows. R will be our consumption rate of nitrogen over -1 because we have a stoichiometry of 1. It can also be equal to the consumption rate of hydrogen over -3 because our stoichiometry is 3. Or if we are expressing it in terms of the product, it would be the production rate of ammonia divided by 2. Another anomaly in the calculation is that recall that we can also express this reaction in different ways. For example, instead of writing it in terms of 1 mole of nitrogen and 3 moles of hydrogen, we could say that to produce 1 mole of ammonia would require half a mole of nitrogen plus 3/2 hydrogen to give us 1 mole of ammonia. And in such a case, our R value will change. Okay, R can be expressed in terms of the consumption rate of nitrogen over -1/2, or in terms of hydrogen, it will be over -3/2. Or in terms of ammonia, it's just the production rate of ammonia divided by 1 because we have a stoichiometry of 1. Okay, so depending on the stoichiometry, our overall reaction rate may be different. However, this is no issue at all because our R value is always dependent on our stoichiometry. And even when we are writing a material balance, we note that Ni out is equal to Ni in plus our stoichiometric coefficient multiplied by R. So we always have an expression of R tied to its particular stoichiometric coefficient. So even if we express our reaction in a different way, our R value may change, but overall it will stay the same. Okay, so let's just start with a simple example. Okay, the reaction of ammonia oxidation over a platinum catalyst follows the stoichiometric equation as shown. As you can see, it's a single reaction. So if we have a reactor, we can envision a reactor with a stream coming in with ammonia and oxygen, and under a given set of reactor conditions, they tell us that 90% conversion of ammonia is obtained. So ultimately we will have ammonia, oxygen, nitrogen oxide and water in the output because the conversion is not complete, so we will have some leftover reactants. And they want us to calculate the output rates of all species from the reactor, and they've given us a feed composition and flow rate, 40 mole % of ammonia and a flow rate of 100 moles per hour. Okay, so they want us to calculate the output rates. So naturally we will require the overall reaction rate in order to achieve that. And since we are dealing with a single reaction system, we can use the simple equation of R being equal to Ni in over -Vi, which I've just shown you. And we can apply the material balance equation, okay, of Ni out being equal to Ni in plus the stoichiometric coefficient multiplied by R. Okay, so using this equation here, we could obtain our R value quite easily. Note that they've given us the conversion of 90%. So more accurately, we are using the following equation, this one here. Okay, our Ni in times Xi over negative Vi. Okay, sorry, this is for a limiting reactant. Okay, so that's for 90% conversion. Okay, and thereafter it's quite simple. We want all of our output flow rates, and it's simply a case of noting the input flow rate Ni in for ammonia and for oxygen, plus our stoichiometry times our overall reaction rate. We get our stoichiometry from the reaction equation. So in the case of ammonia, it will be -4. Okay, so there's our -4 here, multiplied by our reaction rate. In the case of oxygen, it's -5. Okay, we can see the reaction stoichiometry over here. And note that for the products, there are no input flow rates. So we are simply adding our VIR, and we have a stoichiometry of 4 and 6. And so for nitrogen oxide, it's 4 times 9, and for water, it's 6 times 9. Okay, so that's a very simple example, just to get you well acquainted with the material balancing. Now, we can consider the same reaction, but let's assume, however, that we have only 80% conversion, and they've told us that they've provided us with an equimolar mixture of 100 moles per hour, and they want us to calculate the output flow rates as before. Okay, so now instead of giving us a mixture containing 40% of ammonia, we have a 50-50 reactant mixture. And note that because of our stoichiometry, things seem a bit fishy, because if we have a 50-50 mixture but one reactant is being used up more than the other, then there is a possibility that one reactant may get finished or be the limiting reactant. So which one would it be? So to calculate our limiting reactant, even though they have given us a conversion of 80%, we use the same equation that I've shown you before, over negative Vi, and we're assuming a conversion of 1. So in the case of the reaction rate in terms of ammonia, we get 12.5. But if we calculate it in terms of oxygen, we get 10. Okay, and remember, as per the rule, since the R value is lower for the case of oxygen, we can now assume that O2 is the limiting reactant. Okay, and so when they are talking about 80% conversion, we can now assume safely that they are specifying a conversion for oxygen. Because remember that the conversion will always be specified in terms of the limiting reactant. Okay, that is most often the case. Okay, and now calculating the actual reaction rate using our 80% conversion, we get the following. And the rest is applying the simple material balance equation. Ni out is equal to Ni in plus Vi times R, where Vi is the stoichiometric coefficient. Negative in the case of reactants and positive in the case of products.